This discussion is all about density, what it is, and how to calculate it. Density is a mass to volume ratio, and it is an intensive property. And if we go back to thinking about what an intensive property is, it is a property that will not change based on how much matter is present. So it should stay the same regardless of the sample size. So if we're talking about water, water has its own defined density. If you look it up online, it's going to tell you that the density is 1 gram for every cubic centimeter of space that water takes up. So it doesn't matter how much water that you have, the mass to volume ratio will always adjust itself to be 1 gram per cubic centimeter. I would like to introduce you to the density triangle. The density triangle is going to be extremely helpful because it will tell us out of that 3-variable equation, based on what variable that we're solving for, how to actually calculate the unknown variable. So if we know what 2 out of the 3 variables, it's really easy to solve for that third or unknown variable. So density equals mass over volume. So if we cover up the D here, then it's going to tell us to do mass divided by volume. But now if I need to solve for mass, I'm going to cover up the M here, and it's going to tell me to do density times volume. And if I want to solve for volume, or V, I'm going to cover up this V here, and it's going to tell me to do mass divided by density. So based on what variable we need to solve for, we have a real easy way to be able to solve for that unknown variable. You will also see my density triangle in the classroom. So how can density be determined in the lab? Okay, well, if density equals mass over volume, that means we have to know a mass and we have to know a volume. Okay, mass is pretty easy to determine. We can use our scales in class, and our scales will measure our masses in grams. Okay, volume can be found in one of 2 ways. Based on the shape of the object, we will be able to either use a mathematical formula or we will be able to use water displacement. So for irregular shaped objects, things that don't have a mathematical formula to find the volume for, we're going to use a process called water displacement. Okay, and we'll talk about water displacement momentarily. For regular shaped objects like cubes, rectangular prisms, cylinders, we are going to use a ruler to find the desired measurements and plug it into a mathematical equation. So the 2 most common formulas for volumes that we will use in chemistry class are going to be L times W times H, so length times width times height for rectangular prisms and cubes, and our final volume unit will be in cubic centimeters, and then pi r squared times height, so pi times the radius squared times the height for cylinders. So when we solve for volume, volume is either going to be measured in cubic centimeters, which will be the result of finding our volume through using a mathematical formula and using a ruler to make the measurements for the variables in that mathematical formula. Or if we use water displacement, or we're finding the volume of a liquid or solution, our volume unit will be in milliliters. And the great thing about the centimeter and cubed and the milliliter is that they are equivalent. So we don't have to worry about trying to do any converting. Whether we're measuring in cubic centimeters or milliliters, they are the same in terms of the measurement that they provide. Now, with water displacement, this is a process in which an object is submerged in water. And if we look at the difference in water levels before and after we submerge an object that is more dense than the water itself, then that will actually tell us what the volume of that irregular shaped object is. So if you actually take a look here, you're going to see 2 graduated cylinders. We've got a water level before we add an object, and then the water level after we add that object. And like I said, the difference between those 2 water lines are going to be the volume of whatever that object is. when we can find the volume using a mathematical formula like this cylinder here, or when we can do L times W times H for rectangular prisms or cubes, that would be the preferred method, simply because you will find that the ruler will provide more accuracy and precision than the graduated cylinders will in our classroom. Okay, so let's do some example problems. A sample of metal has a mass of 12.90 grams and a volume of 45.0 cubic centimeters. What is the density of this metal? So we're thinking density equals mass divided by volume. And I can simply cover up that D, and it tells me to do M divided by V. Okay, so if we're struggling to figure out what units we have here and what variable belongs to that unit, the 12.90 is a gram measurement or mass measurement, and it's telling us that the volume is going to be 45.0 cubic centimeters. So now I'm going to go ahead and take the 12.90 grams, and I'm going to divide it by 45.0 centimeters cubed. And my calculator is going to give me a nice long number, 0.28666 repeating. Okay, so how do I know how many numbers should go in my final answer? So when we divide, we're looking at the least amount of sig figs. So for the least amount of sig figs, here we have 4 sig figs. And here for our volume measurement, we have 3 sig figs. So we will need to round our final answer to 3 sig figs. I'm going to look at that 6. It's 5 or greater, which is going to round the 6 preceding it up. So my final density of this metal is 0.287 grams per centimeter cubed. So you'll notice here that my units are not like units, so neither one of those will cancel out. How would the following substances arrange themselves in a vertical column like a graduated cylinder? Well, first of all, we need to know a little bit about the densities of each of these substances. So if you can't calculate the densities of them, I would just look up the theoretical densities that you can find online. So for ethanol, the density of ethanol is 0.791 grams per milliliter. Okay, the density of oil is around 0.93 grams per milliliter. The density of water is 1.00 grams per milliliter. And the density of corn syrup is 1.38 grams per milliliter. So the higher the density, the lower on the vertical column, and the lower the density, the higher on the vertical column. So let's go ahead and arrange these. Okay, so the yellow, the corn syrup is the most dense, so that would be like liquid or substance D. Okay, and then the next lowest on the vertical column, or the next highest in terms of density, is going to be the water. So the water will be substance C. And then next, in terms of highest density, okay, or the one that's going to go next on the vertical column is going to be the oil. We know oil is less dense than water, so it usually sits on top of it. So the oil will be substance B. And then ethanol is the least dense, which is a type of alcohol. So that is going to be substance A in the red. So if I ask you questions about whether or not a substance will float, sink, or suspend in another substance, we need to make sure that we understand what that means. So float means that it is less dense, that object is less dense than the substance that it is contained in. So if this is water, for example, this liquid, then we would have to say that the density of whatever that object has to be less than 1.0 grams per milliliter or grams per cubic centimeter. If we're talking about sinking, that means that the density of whatever that object is has to be greater than 1.0 grams per milliliter. Now, if I talk about suspensions, if something is suspending in the water, that means that it has a density right around 1 gram per cubic centimeter or milliliter, or whatever that substance may be. What is the volume of a piece of zinc with a mass of 25.69 grams? The theoretical density of zinc is 7.14 grams per milliliter. Okay, so I'm solving for volume. And when I solve for volume, then I need to do mass divided by density mathematically. So I know my mass, and I know my density. So I simply need to take 25.69 grams, and I need to divide by 7.14 grams per milliliter. Okay, and my grams are going to cancel. If I multiplied by the reciprocal, then my milliliters would then be on the top of that ratio. So when I plug that into my calculator, I am getting an answer of 3.59803 and a bunch of other sig figs. But remember, when we multiply or divide, we use the least amount of sig figs. So I have 4 sig figs in my mass and 3 in my volume. So I am limited to recording 3 sig figs in my final answer. So I'm going to look at that 4th sig fig, which is going to round the number 9 preceding it up, which in turn is going to round my 5 up. So my answer should be 3.60 milliliters of space. If a solid has a density of 5.21 grams per milliliter and a volume of 325.0 milliliters, what is the mass of the solid object? Okay, so I'm solving for mass, which means I need to do density times volume mathematically. So I am given the density of whatever the substance is, and I'm also given my volume. So really I just need to plug these numbers into my equation. So M equals 5.21 grams over milliliters. So there's my density. And now I'm going to multiply by my volume, which is 325.0 milliliters. And you can see my like terms cancel. So milliliters and milliliters. And my calculator is telling me that it's 1,693.25. Okay, and that's too many sig figs. I'm going to use the least amount. So I have 3 sig figs in my density, and I have 4 in my volume. So I'm limited to 3 sig figs. So I'm going to look at my 4th sig fig, which is less than 5, so that keeps that number preceding it the same. So my answer should be 1,690 for my mass measurement. Okay, remember I need to keep that last 0 as a placeholder. The water level in a graduated cylinder stands at 13.5 milliliters before a copper sample is lowered into the cylinder. The water level then rises to 19.8 milliliters after the sample is submerged. What is the mass of the sample? The density of copper is 8.96 grams per cubic centimeter. So I am solving for mass of the sample, which means I need to do density times volume. Okay, so it looks like I am provided with the density here. Okay, but I don't necessarily know my volume yet. Okay, I'm going to use the process of water displacement. So I have an initial volume of my water level being at 13.5 milliliters. And then when I drop a copper sample, which is more dense than the water itself, then my water level is going to rise. So my final volume of my water level is going to be 19.8 milliliters. So if I do V final minus V initial, that is going to give me the volume of the copper sample, which happens to be 19.8 milliliters minus 13.5 milliliters, which gives me, and remember when we're looking at sig figs, when we add or subtract numbers to the right of the decimal, so I have one number to the right of the decimal. So my final volume is 6.3 milliliters. Okay, so now I can go ahead and finish up this problem. My density is 8.96 grams per centimeter cubed. And I'm going to take that density and I'm going to multiply by the volume found through water displacement, which is 6.3 cubic centimeters. Okay, remember this is kind of confusing because we solved in milliliters, but we need to remember that 1 milliliter is the same as 1 cubic centimeter. So in order to get those cubic centimeters to cancel out right now, I'm just going to say that the volume is in cubic centimeters, or if you prefer to change this here to milliliters and keep everything in milliliters, that's also the same. So it shouldn't change anything mathematically. All right, and now my centimeters cancel. My calculator is giving me an answer of 56.448. Okay, but I'm going to go ahead and limit it to 2 sig figs because my volume is 2 sig figs and my density is 3 sig figs. So with 2 significant figures, my answer should be 56 grams. When collecting a series of data points, for example, a bunch of different densities, the terms accuracy and precision can be used to discuss and analyze those results. Accuracy is the ability of a tool or technique to measure close to the accepted value of its quality, or its quantity being measured. So how close it is to being correct. So if you are accurate, you are super close to what the theoretical or the correct value is supposed to be. You are not accurate if you are not close. Precision, on the other hand, is a word used to measure how close your data points are to one another. Not necessarily how close they are to the true or accepted value, but how close they are to one another. The way that I like to discuss precision and accuracy is in terms of thinking about throwing darts at a dartboard. We always think of that coveted spot on the dartboard as the bullseye. So this is the accuracy point. This is the point at which we are trying to aim at. Okay, so if I'm looking at scenario number 1, I threw 4 darts. 1, 2, 3, 4. And if I'm going to talk about accuracy, I would say I'm not accurate because I did not hit, for any of those 4 data points, the bullseye. I also don't think I'm very precise because my 4 data points are not close to each other. So accuracy is the ability to hit the bullseye. Precision is the ability of my data points to be close to one another. So I would say that none of my data points are accurate, and I am not showing any precision with my data points either. Okay, for the second scenario, I'm trying to hit the bullseye, and I did not hit the bullseye out of those 4 darts that I threw, not even once. So I'm definitely not accurate, but I would say that I am precise because if you look at my 4 data points, they are pretty close to one another. My last scenario, I would say my 4 data points are accurate because they're close to the bullseye. I would also say I'm precise because those 4 data points or darts are close to one another. You can always single out a specific data point when talking about accuracy. So you can say 1 out of 4 darts are accurate or 2 out of 4 darts, but you cannot talk about precision unless you have at least 2 data points to compare to one another. Here is another scenario where we can describe the results in terms of accuracy and precision. A student measured a magnesium strip 3 times and recorded the following measurements using the centimeter ruler: 5.49 centimeters, 5.48 centimeters, and 5.50 centimeters. The actual length of the strip is 5.98 centimeters. Describe the results in terms of accuracy and precision. Okay, well, I would say at this point, looking at those 3 data points, they are very precise because all 3 of them are very close to one another. But in terms of accuracy, I think that they are almost 0.50 centimeters away from that theoretical or actual length of the strip. So in terms of accuracy, I would say none of my points are accurate, but in terms of precision, I would say my data points are precise. You might be wondering, how close does it need to be from that theoretical value to call it accurate? Knowing how our centimeter rulers go to the hundredths place, I feel like we can be a heck of a lot closer. If you're within under 5% error, then I would say you can maybe talk about your points in terms of accuracy. But if you're not under 5% error, then I would say to not use that term. So how can we calculate percentage of error? How do we know if we're under 5% or not? Okay, well, no one likes to talk about how wrong they are, but this is a quantitative way for us to reason how close we are to the true or accepted value. Okay, so we'd like to be under 5%. That's our goal, but we're not always going to get there, unfortunately. So once your densities are determined experimentally, you've done all your number crunching, then you can compare your lab results to the theoretical value, which is the value that would be published or the value given by your teacher using the following equation. Okay, so percent error equals the absolute value of the theoretical minus experimental results, then divided by theoretical, and multiply by 100 to make the percent. Once again, theoretical results are given by a teacher or can be looked at online or through a journal. So that is what the results are supposed to show. And then experimental results are from the lab.